So section 8.1 deals with the development of the periodic table, and there's 4 individuals to credit. It's important to keep in mind that the periodic table wasn't developed by just one person. These 4 individuals contributed a part to the overall formation. So the first one would be John Newlands. And he noticed that when the elements were arranged in order of atomic mass, every 8th element had similar properties. He identified this correlation as the law of octaves. However, the scientific community rejected his idea. The second individual to credit is Dmitry Mendeleev, and his system of classification was way more improved than Newland's, and the reason being is because the way he arranged the elements showed similar properties among the second individual to credit is Dmitry Mendeleev, and his way of classifying the elements was a greater improvement than Newland's. And the reason being is because he grouped the elements more accurately according to the properties, and secondly because he was able to, the way he classified the elements led to a prediction to the properties of the future elements that had not yet been discovered. The third individual to credit is Rutherford, and he estimated the number of positive charges in the nucleus of a few elements. However, the significance of these numbers was overlooked for several more years. And the last individual to credit is Henry Moseley, and he discovered a correlation between the atomic number and the frequency of X-rays, and he used this equation to solve for that. And I think that's it. And he used this equation to solve for that. So in the end, the formation of the periodic table led to groups and families and periods having the number of electron orbitals correlate to one another, similar characteristics, and the same number of valence electrons, depending on the group. So section 8.2 deals with the classification of the elements. So to begin with, for representative elements, this refers to groups 1A through 7A. So it would include these. And these groups all have incompletely filled S or P subshells of the highest principal quantum number. For noble gases, this would include group 8A, except it excludes helium, and these all have completely filled P subshells. For the transition metals, that would include all of these transition elements. And these have incompletely filled D subshells, or readily produce cations with incompletely filled D subshells. For lambenites, that would be these. For lambenites, that would include these, and actinides would be these. They're sometimes called the F block transition elements because they have incompletely filled F subshells. The first definition the book goes through is valence electrons, and this refers to the outermost electrons. So depending on the group you're in, you would have the same number of valence electrons. So group 1A would have 1 valence electron. The second definition the book goes through is core electrons, and this refers to all the non-valence electrons in an atom. So this question asks how many valence electrons are in the alkali metals, halogens, and alkali earth metals. So like mentioned before, the number of valence electrons refers to the group you're in. Well, not refers, but depends on the group you're in. So for the first one, alkali metals, that would be group 1A, and they would have one valence electron. For the alkali earth metals, that would be group 2A, and they would have two valence electrons. And for the halogens, that would be group 7A, and they would have 7 valence electrons.
I'll be going over section 8.3 and 8.4, which is the periodic variation in physical properties and ionization energy. Two of the vocab words that are going to be the most important for problems that are going to be solved later is ionic radius, which is the radius of a cation and anion, and ionization energy, the minimum energy required to remove an electron from a gaseous atom in its ground state. And so our first problem is, here's a list of assorted ions written in alphabetical order. Aluminum 3, fluorine, magnesium, nitrogen, oxygen, and sodium. So to make life easier, we first sort them in the order that they are in on the periodic table, which is nitrogen, oxygen, fluorine, sodium, magnesium, and aluminum. These are all isoelectronic with a structure of 2,8. The smallest ion will be the one with the largest number of protons, which is aluminum, and the biggest is the one with the least amount of protons, and 3. So smallest to largest would be aluminum, magnesium, sodium, fluorine, oxygen, and nitrogen. The next one wants us to explain the difference in first ionization energy between lithium and beryllium. So we're going to need the periodic table for this. So as we travel across the periodic table, the atomic number increases because the number of protons are increasing with each consecutive atom. With the increase in protons comes an increase in nuclear charge. The nucleus in the beryllium atom has a greater positive charge, thus wants to hold on more tightly to the 2 electrons located in the 2s sublevel. No additional electrons are added to the inner core, so no additional shielding takes place. Therefore, beryllium requires more ionization energy to remove the first electron in the second sublevel. So another vocab word that we're going to end up needing is effective nuclear charge, which is the nuclear charge felt by an electron when both the nuclear charge, which is represented by Z, and the effects of the other electrons are taken into account. So this is the equation that we're going to be using, and it's for effective nuclear charge. And so what we're going to find is the effective nuclear charge for neon, sodium, and fluorine. So we're going to start by figuring out how many non-valence electrons each one has, which can be figured out from its electron configuration. Neon has 10 electrons, so the configuration would be 1s2, 2s2, and 2p6. The valence shell is 2 and contains 8 electrons. Thus, the number of non-valence electrons is 2, because 10 total minus 8 goes 2. So the atomic number for neon is 10. So setting up the equation, 10 minus 2 equals 8. Fluorine has 9 electrons, but because it's fluorine's negative, it gains an electron, so it has 10 electrons. The electron configuration is the same as for neon, and the numbers of non-valence electrons is 2. So 1s2, 2s2, and 2p6. And the atomic number for fluorine is 9. So, setting up the equation, 9 minus 2 equals 7. Now, sodium has 11 electrons, but because it's a positive ion, it's lost an electron, so minus 1 equals 10. Because it's 10, the electron configuration is the same, 1s2, 2s2, and 2p6. So the atomic number for sodium is 11, so when we set up the equation, equals 11 minus 2 equals 9 plus. So in each of these examples, an atom of 10 electrons, each atom has 10 electrons, but the effective nuclear charge varies because each has a different atomic number. The sodium cation has the largest effective nuclear charge, which results in the electrons being held the tightest, and therefore sodium has the smallest atomic radius. Alright, now for the last problem, the vocab word that we're going to need is isoelectronic, which means the ions have the same number of electrons in the same arrangement. So this problem, it gives us the ions sodium, magnesium, and aluminum. There's all supposedly isocentric. I've already explained what that meant. So now I need to find and state the electronic structures of these 3 ions and explain why that the radius falls as we go across the period. So all these structures have 2,8 isoelectronic. And because all the electronic structures are the same within both sets, the outer electrons must have identical screening. So as we go from sodium to magnesium to aluminum, the number of protons in the nucleus increases. So the pull of the outer electrons pulls the outer electrons in more and more. And the same thing is true for other sets of ions as well.
I'll be covering section 8.5, electron affinity, for chapter 8. Electron affinity is equivalent to the energy required to remove an electron from an anion. It also increases from left to right across the periodic table with little variation within a group or family of elements. Additionally, nonmetals tend to have higher electron affinity than metals do. The few variations that occur for electron affinity are usually tied to electron configurations on the outermost shell of an atom, i.e., dealing with their valence electrons. The configuration may contribute to electron shielding in such a way that increases the electrostatic force felt by incoming electrons, thereby decreasing the likelihood of bonding. Question 1. Does lithium or beryllium have a greater electron affinity? At first glance, beryllium seems more likely to have a higher affinity, since both are metals, and beryllium is further to the right of lithium, which would fit the overall trend. However, lithium actually has a higher affinity value than beryllium, due to their electron configurations. Lithium will fill its 2s shell with an additional electron, but by contrast, beryllium will have opened its new 2p shell since it already had a filled 2s shell, which will make it more unstable than lithium. Question 2. Consider the electron affinities of elements in period 3 starting with aluminum. Which elements conflict with electron affinities overall trend? All the elements starting with aluminum and continuing right appear to coincide with increasing affinities from left to right, except for phosphorus, whose affinity dips between silicon and sulfur. The reason for this is again due to electron configurations. If an electron were placed in phosphorus's next available orbital, it would experience more electrostatic repulsion than the other elements in the list. This is due to there already being 3 electrons in the p shell, meaning the 4th electron will be placed beside another electron requiring a different spin. By contrast, silicon's group would not offer any additional resistance and would become more stable with the NP3 shell being filled. Negative electron affinity since it is already stable. By contrast, as a halogen, fluorine would greatly require an electron. Finally, hydrogen is further to the left of the periodic table than carbon, and so we'd beat xenon, but not to the extent that it would overtake carbon or fluorine. Here you can see the elements arranged. Xenon as a noble gas, fluorine as a halogen, hydrogen, a lone nonmetal, and finally carbon as a nonmetal. Question 4. Would you expect an alkali metal or a halogen to have a higher electron affinity? The answer is halogen because they are further to the right of the periodic table and are nonmetals, which contrasts with the fact that alkali metals are metals, and nonmetals tend to have higher electron affinities than metals.
So the section I'll be covering is section 8.6, which is variation in chemical properties of the representative elements. And the first thing that we're going to be going over is the trends in chemical properties. So the first thing mentioned in the book is are the different chemical behaviors and their trends. So the first kind of trend that is described in the book is a diagonal relationship. And the diagonal relationship are similarities between pairs of elements in different groups and periods of the periodic table. So basically what this is saying is that elements show similarities to elements that are located diagonally below them in the periodic table, such as lithium, boron, magnesium, and silicon. So the group 1A elements that include lithium, sodium, potassium, carbon, CF. These are known as the alkali metals. And they have low ionization energies. And they are all also very reactive. An alkali metal also reacts with water to create hydrogen gas. They lose their shiny appearance as they combine with oxygen gas to form oxides. For example, if lithium were to react with oxygen, we would get lithium oxide. The reason that different types of oxides are formed when an alkali metal reacts with oxygen has to do with the stability of the oxides in a solid state. which depends on how strongly the cation and ions attract to one another. So lithium tends to perform predominantly lithium oxide because this compound right here, this compound is more stable than lithium peroxide. So in group 2, we have the alkali. We have the alkali earth metals. And these metals are less reactive than the alkali metals. The group 2 elements include magnesium, so the ionization between these two decrease from beryllium to from beryllium to barium, the ionization decreases. The reaction that these elements have with water are little to none. For example, if barium were to react with water, it would only be strong enough to attack the water. As far as calcium and strontium, these have very interesting characteristics. That is because strontium 90 is a very radioactive isotope and is a major product of an atomic bomb. And as far as calcium, these are found in our bones. High exposure of this element in our bodies can lead to chronic illnesses. So the next group is group 3A, and the elements that are included are boron, aluminum, all of these elements are metalloids. So when these elements are exposed to oxygen gas, for example boron, would be unreactive towards oxygen gas and water because it does not form binary ionic compounds. However, for aluminum, when it is exposed to oxygen gas, it creates aluminum oxide. The group 3A metallic elements form both unipositive and tripositive ions moving down the group. And the unipositive ions will become more stable than the tripositive ions. They also form many molecular compounds. For example, aluminum reacting with hydrogen will form AlH3. So from left to right on the table, on the periodic table, we're seeing a shift from metallic to non-metallic characteristics that will represent the elements. In group 4A, the elements that are included in group 4A are carbon, silicon, As far as the characteristics, carbon is a nonmetal. These two elements are metalloids. And finally, these two will be metals. As far as reactions, they do not react with water, but they do react with acids. As far as reactions, these two elements do not react with water, but they do react with acids. So the group 4A elements do create compounds, and the oxidation that they use is +2 and +4. For carbon and silicon, it would be +4 ionization, +4 oxidization, and the +4 oxidation is highly more stable than the +2 oxidizing. The lead element would be a +2 oxidization. And finally, the outer electron configuration of lead would be the outer electron configuration of lead would be 6s2 6p2. So as shown, the group 5 elements contain nitrogen, phosphorus, This happens when the following oxides react with water. Okay, so going over group 6, we have these elements, so oxygen, sulfur, and selenium will be known as nonmetals, and these last two elements will be metalloids. So the oxygen likes to receive 2 electrons, so the oxidization would be as shown right here. However, this element right here is very radioactive, so there is not a lot of information or studies on it, and they both have a 3D structure. So going on to group 7A, we have these elements which are all nonmetals, and they're all halogens. So this element right here is very radioactive, as well as the elements over here. So there is not a lot of information on them as well. However, chlorine is very reactive, and when involved in a reaction with fluorine, it tends to explode. However, if you substitute it with chlorine, then it would be less of a reaction or substitute. Okay, so group A is known as the noble gases, and they include and all of these elements have a complete outer shell, which gives them a lot of stability, and they all have very strong oxidizing agents, and they bring a lot of interest to chemists because of their stability and their strong oxidization. Okay, just to go further into the periodic table, the properties of oxidization. Across the period, which is going left to right on the periodic table. Okay, so on the left side of the periodic table, we'll find more ionic type compounds. However, on the right, we find molecular. And as far as temperatures, melting point, and boiling point, on the left, we'll find higher. And on the right, we will find lower. As far as acidity, on the left side of the periodic table, we'll find more basic acidity. However, on the right side, we would find more acidic.